In this webinar, first of all, I would like to talk something on this part, general relativity and the space-time curvature, because the entire scenario of astrophysics and cosmology that we are studying today started many, many years back. I think 2015, we celebrated 100 years of general theory of relativity. And this time we are also more than, 2015 to almost 110 years into general relativity. So I would just like to give you a basic idea of general relativity on a very gross way. If you want to know the mathematical part, then you need to go to my channel where you can find out a lot of videos which are there. Okay, so where do we go from here? Is this screen visible? The picture of Einstein and the apple falling? Can you just tell me yes or no?
Yes, it's
okay, fine. So general relativity is a geometric theory of gravitation. Let us remember this one, that other than any other theories, this is something which is a geometric theory. That means we rely mostly on what is called geometry. Definitely mathematics is there, but geometry is predominant. So it is basically the current description of gravity in modern physics. What does that mean? I was just listening to a podcast of Professor Leonard Susskind, you know, the father of string theory, who worked with Ashok Sen also. So it is now understood that general relativity gives us a fairly good understanding of gravity, astronomy, astrophysics, and space science. But it is the current description. That means it might happen that we get a better theory of gravity once it is united with string theory and any other. Also, general relativity, what it tells is that it refines Newton's law of universal gravitation. That means I find most of the students and subscribers, they come to me and tell that, sir, Einstein proved Newton wrong. Newton proved Galileo wrong. No, nobody proved anybody wrong. It is just a refinement. It is a betterment that this theory had got certain limitations, and this theory is improving and refining on that, right? So it is a refining of Newton's theory. It is not wrong. And it provides a unified description in a four-dimensional space-time. So from here, what we understand is that as we move from Galileo to Newton and to Einstein, there is a huge change which has happened. And this change is reflected in astronomy, space science, everywhere. And this had led to a new understanding of everything: mathematics, relativity, science, technology, GPS system, everything. Now, as we move from Galileo to Newton to Einstein, we need to know what are those changes. That means what actually changed. We understand there have been a lot of changes, but what are those changes? The first change that we see is that Newtonian gravity, which actually deals with 2-point particles, M1 and M2, or maybe M3 or M4, whatever, it got changed to space-time curvature. That means we do not deal with forces. There are no force now. Although Newtonian gravity was redefined by Lagrangian mechanics and by Poisson equation, recently I had a class on my channel on Poisson equation. Why we need a Poisson equation if Newton's laws are fine? We need Poisson equation because we are not dealing with specific point particles, but as a field, okay, which is spread out. There are n number of particles. How will we deal with M1 and M2 and M3 and M4? So we do deal with Poisson equation or Lagrangian mechanics. Now we call it as a space-time curvature. And this space-time curvature is further extended in what are called black holes. This is the first change which we have, right? The second change that we have is that the entire geometry changed. Why? Because we don't deal with straight lines. Straight lines were what we were taught in our school days: Cartesian coordinates, A, B, C, angles, theta, etc. But now we deal with geodesics. I will cover up geodesics. Geodesics are straight lines, but they are not straight lines. They are curved lines on a sphere or any surface. And because these things have changed from straight line to curved spaces, so we need a new geometry. Not the usual geometry of Euclid's axiom will follow. So what we do is differential geometry. This is a new change which has come up. Okay. The next change what we get is this one. This is a very interesting, very important change. In Newton's time, we dealt with three-dimensional of space, the length, breadth, and height. But time was independent. Time was never a coordinate, or Newton never thought that time will be included in a coordinate system. Einstein unified it in a four-dimensional space-time. So technically in differential geometry's term, we call it as a manifold. A surface which has got many folds and curvatures is called a manifold. This is a wrong definition, but just to tell you, manifold is something which deals with a four-dimensional space-time. Now, in order to deal with this type of a four-dimensional space-time, we need something beyond vectors. Vectors cannot deal with four-dimensional space-time. So mathematicians invented what is called four vectors. I think most of you know what are four vectors. So there are three-dimension space and one-dimension time. And the four vectors were especially good in special relativity. Electromagnetic four vectors. There are a lot of four vectors were there. Lorentz transformation, etc. And even we found that the four vectors are causing a problem, because electromagnetic field tensor, Riemann curvature tensor, these things cannot be dealt with four vectors. So what we need is a tensor. I don't want you to learn tensors right now. I've got a lot of videos on my channel dealing with tensors step by step. You can look over there. But this is again a change, that from four vectors we move to tensors. And now you see the final change, that the classical laws of motion, F equals to ma, or Euler-Lagrange equation, whatever we call as classical law, now is dealing with relativistic law, which we call geodesic equation. That means same, the straight line, point particle moving from this part to this part, same thing is happening, but on a curved surface. Things are moving on a curved surface. So F equals to ma or Euler-Lagrange equation won't give us that value. So we need this kind of a very weird looking, but it is very simple. It is called a geodesic equation. Also, the classical laws of gravity, as I told you, M1, M2, M3, if there are n number of particles, Newton's law won't work out. So we come to what is called the relativistic law of gravity, and this is actually dealt with Einstein Field Equations. So these are the major changes which happened, from straight line to curvature, from geodesics, this, that, four vectors, tensors. So this is a kind of a change which happened when we started moving from Newton's law to the new world of space and astroscience and astrophysics, that is the curvature of space-time. Okay, just a quick request. Are you all okay with me? I mean to say, till now everything is going fine? You can listen, you can follow me?
Yeah, yes.
Okay, I have a habit because I keep on doing this in my classes, so don't take me wrong. Okay, so now we start that, okay, how did it all began? That means this curvature and these changes, etc., how it started. I won't take you much in history because I know you're all science graduates, but just to tell you a very quick and a very interesting history. Now, this picture that you are seeing, you can identify one as Albert Einstein. Can you recognize the person on the extreme left-hand side, the yellow box? Can anybody tell me who this person was?
Nikola Tesla. I
No,
think so.
this was Marcel Grossman.
Okay.
Okay, Marcel Grossman, he looks like Nikola Tesla, absolutely. But this is Marcel Grossman. Marcel Grossman was a very close friend of Albert Einstein. And to tell you a very important fact is that Einstein was never aware about tensor calculus. Okay, if you go to my channel, you will see there are many videos where Einstein has told that my friend Marcel Grossman actually helped me. Now, this picture is of Marcel Grossman, who was an expert of differential geometry, which we are talking about, this curved surface. Einstein was more of a physicist. He was never a mathematician. So this was a paper which I won't dare to read. This is in German, and it calls the outline of a generalized theory of relativity. That means when Einstein came back from Prague and joined the Zurich Polytechnic in 1913, I'm talking Switzerland, he and Marcel Grossman first started to think that how we can improve special theory of relativity and give a general theory of relativity. It's a very important paper. It is called Entwurf document. That means the draft. Entwurf in German means draft. But there was a problem with this this paper, because as I have written, it did not carry the covariant theory of gravity. In tensors, those who know tensor calculus, we have a covariant tensor, a contravariant tensor, and a mixed tensor, right? So Einstein was unable to find out what is called the covariant theory of gravity, and Marcel Grossman was helping. Marcel Grossman was younger to Albert Einstein, but he died much earlier to Einstein, right? So Marcel Grossman actually helped Einstein to form what is called the general theory of relativity, which we talk of Einstein and space-time curvature. So remember, Einstein's tutor was Marcel Grossman. If you go to my channel, you will see there is a small YouTube short video which I have made. Who was Einstein's tutor? Okay, one was his wife, Mileva Maric, obviously, and another was Marcel Grossman. Very interesting history. So here you see, finally what happened is that this report came up in 1915. Now, there was a debate that who published earlier. Was it David Hilbert or Albert Einstein? We are not going into debate. We are science students, right? So let us forget the debate. And in 1915, this was the paper during that time, because Prussia was an independent country. Second World War was not going on. So it is called the Royal Prussian Academy, where he presented this paper. This is the paper, the yellow one, which you can see on the screen, is basically the original paper of Albert Einstein. Okay, and it actually proved these things. First of all, there was a problem with the calculation of the shift of Mercury, which is called the perihelion precession of Mercury, right? This was corrected, and it was very minute, very small, 43 arc seconds, but it was quite a good amount. I mean to say, if you calculate 43 plus 43 over a century, then it creates a lot of anomaly, a lot of difference. And I remember this day, 29th of May, 1919, when Arthur Eddington first made an experiment showing that the light of a star is actually bending. Is it that the light of a star is bending? No. But due to curvature, the light seems to travel the other way around. Instead of coming straight, it is causing a curvature. So what does that mean? It proved Einstein's theory of gravity to be correct, that yes, there is a space, there is a mass, for example, a heavy ball, and it creates a curvature. So that is why the light is traveling a little bit off the way. It is traveling in a curved space. And here you see, that was what I was talking about. Whenever you search for general theory of relativity anywhere on Google, etc., you come upon this type of a photograph. Okay, there is a mass and there is a space which is bending, etc. So what it actually tells, that if you type out this word general relativity, always you will get this kind of a thing. Wikipedia, New Scientist, everyone would show this type of a curve. That means what I told you right at the beginning, the very first slide, that general relativity is a study of geometry. So this slide actually shows that it is a study of geometry. That is why there is a dent, there is a mass, and it causes a curvature. Okay. So remember that it is a study on the curvature of space-time caused by the mass and energy. This is basically what it is. How, if you take a bed sheet, you hold and your father holds, and let your mom put a heavy ball in it, you will see it will cause a dent. Okay. And if you throw a ball, it will curve down until it reaches another point. Simple. So a heavy mass causing a dent. The more heavy it is, more will be. If you put a very heavy mass, your bed sheet will tear up. Right? So this is the study of what we call curvature of space-time. Now, this study actually is what is called, I'm so sorry. This is the study which is called this one. Now, just first concentrate on the left-hand side. The left-hand side, what is called a Minkowski space-time, forget the term. It was actually by Einstein's teacher, Hermann Minkowski. You see, all the lines are very flat. Straight lines. Okay, light cone, etc. Don't worry, I'm not going to cover this. But you can see that in general relativity, it is causing a kind of a curvature. So imagine now the right-hand side, if there is a small red point, which is moving from one point to another. Okay, if I am standing out of the screen, now see this screen now. Okay, so the person who is standing outside the screen, he sees that there is an acceleration. That means something is pushing the point from this to this, and that is why the point is moving. But the fact is that there is no acceleration. There is nothing. There is no force at all. And just because the sphere is curved, the particle is moving from this point to this point. Now, Shubhankar and others who are in space science and who are designing rockets and satellite, you know how important this curvature is. Until you calculate the curvature, all your satellites and all your links movement will fail. So this is a very important step for us to understand. In 1915, I'm talking. A person standing outside will think that there is something which is pushing the ball or the red dot. But the fact is that nothing is pushing. The ball is moving in the straightest possible path, in the straight line. But because the sphere is curved, it seems that it is moving in a curved space. This is what is called a geodesic. So you can just quickly, go through. Curved space-time means it is physically bent. No. Objects feel a force. No. Objects actually follow the natural path. And general relativity is only about black holes and extreme gravity. No. Even Earth and Sun and anything which is very heavy can cause a curvature. So now, concentrate on the left-hand side of what I have written, left-hand side bottom of the screen. Misconception arises because we tend to think gravity as a force rather than a geometry of space-time curvature. This very essence that gravity is not a force, but a curvature of space-time actually was a big step for Einstein, and it forever changed our understanding of space, mathematics, satellite, designing, everything. Okay, so you are all okay till now? Rajkumar, Karan, Pramananda, Swapna Sagar, you are enjoying this? Till now everything is fine?
Yes, sir.
Okay.
Yes.
Okay, great. So this is what is guided by this one, which is called super. Okay, thank you very much. Einstein field equation. Now, you might say that why do we need this equation? Obviously, we need this equation. Otherwise, how can we calculate the curvature, all those lines, etc.? I'm not going to go deep in there. If you go to my channel, you will find a lot of good videos on Einstein field equation because it takes almost 1 hour to explain each and every component. I will just give you a basic idea. This is how the Einstein equation looks like. Now, remember, this is one of the form. This is not a very common form. If you go to internet, you will find a different form, G, mu, nu, etc. Okay, but this is a very common form. So the left-hand side of the entire equation tells how the space-time is curved. That means how much or how will I measure those curvature. And the right-hand side tells that what causes the curvature. So your mother is throwing a heavy ball on the bed sheet. You and your father is holding that. So that heavy ball which your mother is throwing, that is the right-hand side. And all the measurements and problems that arises, this is the left-hand side. So that is why I have written right at the bottom, space-time tells matter how to move and matter tells space-time how to curve. This is not me. This is a famous physicist by the name of A.H. Wheeler. He has actually quoted this line. So what does this equation mean? Let me quickly get through. So you already know certain parts of the equation. Lambda is a cosmological constant. Now we use this lambda to learn dark matter. Okay. 8 pi is the constant, right? Pi is basically because we are measuring the area of this what we call sphere. So it automatically arises. G is the gravitational constant, and C4 is basically the speed of light. Now, why it is c to the power 4? Obviously, there are 3 dimensions of time, space, and 1 dimension of time, special relativity. So obviously, it has to be C4. These are the things which you already know. Lambda, 8 pi, G, C4. What you don't know are this. Okay, I will just quickly go through. I will give you a pictorial understanding. Ricci curvature tensor R. It tells how a volume of matter changes. Ricci scalar, how a ball deviates. Metric tensor, causal structure of space-time. Riemann curvature, another kind of a curvature. And stress energy momentum tensor, movement of space-time. Don't worry about these terms. I will just explain you in a picture which will make you understand quickly. Okay. Now, this mu nu, remember, these mu nu are dimensions of space-time. So, Swapna Sagar or anybody can count. How many mu nus are there on the equation? Can anybody count? One is R. How many are there?
4.
4 plus 4 plus 4 plus 4. So how many total? Total how many mu nu?
16.
16. Yeah. That means this equation is basically showing us that there are 16 dimensional partial differential equations. The first mu nu, length, breadth, height, time. Again, length, breadth, height, time. In this way, 16. But if you go later to my channel, you will see we don't deal with 16 partial differential equations. Out of them, 6 are common. So we deal with 10 equations. So mu nu's are basically dimensions of space-time. Just on a wall, as we write space and time, x and y, these are space-time. Okay, first let me show you, this is the thing. So each mu nu, actually 0 is time, 1 is x, 2 is y, and 3 is z-axis. So total, we are dealing with 16 partial nonlinear differential equations. Quickly, let us understand the first R, which is called the Ricci curvature tensor. Now you see, if I move a ball in a flat space, there is no deviation. It moves straight. That means Ricci tensor is 0. If it is like a sphere, if we move that ball, it will slowly become small. The second one. So Ricci curvature is greater than 0. And if it is spread out like this, the ball will increase in size. So Ricci tensor is less than 0. So how a ball moves in a curved space, this is what Ricci curvature tensor measures. But it is not that simple. I've given you a very basic idea. So the first R is clear for you, Ricci curvature tensor. Now you see the metric tensor, the G. This is in a curved space, how close the curvature is and how loose the curvature is. You know, you can just think it in this way, that if you are measuring distances between 2 points, for example, this point to this point, if you want to measure a distance, how will you do? You will just draw straight lines and angles, etc. But in a curved space, it is not that simple. So understand that metric tensor measures the distances, angles, the way we do on a piece of paper. But it is highly complex because here the lines are not straight, and the curvature is also sometimes very close, sometimes very loose, etc. So this is what is called the metric tensor. Now, so up till this one, you know, this first R you have learned, okay, this one, then the second R and the G. So first you learned what is the Ricci curvature, then the metric tensor. Now we come, what I was telling, that if your mother is throwing a ball on the bed sheet, this is the stress energy momentum tensor. What does that mean? It means that everything related to matter, whether it is momentum, density, stress, pressure, anything which constitutes a matter. What is a matter? For example, this box is a matter. So if I take this box, there is a stress. Yes, you can ask your question, Paramananda. You have a question? Please tell me.
Okay, no, sir. I will ask it later. Okay, sir.
Okay, fine. So if I take an object, then this object has got a stress, it has got an energy, it has got a density, everything in this box. How we are calculating that? That is what is the stress energy momentum tensor tells. Here you can see, if I plot the stress energy momentum tensor, that means make it very simple because it is a tensor equation. You will find these things. Energy density, responsible for curvature. Pressure also causes curvature. Energy flux, movement of matter, also causes curvature. So everything that a matter, a simple ball or a metal ball or a cricket bat or anything which makes up, this is what is called the stress energy momentum tensor. And also you will see that there is momentum density, etc. So overall, what we can say is that all these factors are now in a tensor-like box, which actually helps us to understand that how much matter, how much things are changing, what is the density, flux, pressure, etc. And here it is. This is a famous analogy. I think you have heard about Professor Amol Kumar Roy Chaudhary, the famous Roy Chaudhary equation, right? Which Professor Madhu Krishna in Agnirath earlier episode has explained, actually, the Roy Chaudhary equation. So what it tells is that if you tell a tram which is on a tram depot, and if you ask that which way the tram will go, so if you ask a physicist, they will tell you, give the initial position and momentum and the first order differential equation, I can tell you where the tram will go. But Einstein or Professor Roy Chaudhary explained it in this way. No, the tram will follow the path which is laid. That means if the path is curved, it will go in a curved path. If it is going this way, it will go in this way. Simple. No position and momentum. So that means, again, this is a very good example. Try to understand that position and momentum means what? Mass, point particles, that is a problem. So Einstein told it in this way, that let us not talk about position, momentum, etc. The tram will follow its natural path. If you ask a child who has just started to walk, which way the child will go, this way or that, you cannot predict. It will follow its natural path. So the tram will follow the natural path, which is curved or straight. This is what is called a geodesic. And what causes this change? The matter, that is the stress energy tensor. And as it moves along the path, which is curved, in Newtonian mechanics, we call it straight line. Okay, this is what we call as a gravity. This effect is what is called a gravity. So up till now, what we have learned is that we have learned Einstein field equation. We learned what causes general relativity, a little bit of history, and how this curvature is being calculated through Einstein field equations. Now, the big question is that, okay, we learned everything, but how does it help? Does it really have anything to do? Does it help anything? Yes, it does. And this is the answer. Now, here you see, if I take Jupiter, okay, so 1 kilogram on Earth would weigh this much, 24.79 Newton on Jupiter. So that is why the gravitational acceleration of Jupiter is highest. On Earth, 1 kg is this much. So gravitational acceleration is this much. On Mercury, it is even less, 3.71 Newton. So what I am trying to tell from this diagram is that now we will not think G or acceleration, gravity acceleration as a force. The bigger the mass, Jupiter is very big, so it causes a lot of curvature. Lot of curvature means in Einstein's language, it is basically gravity. Less curvature means less gravity. So I mean to say this is how we learn. Okay, yeah, Rajkumar, tell me your question.
Sir, can you go to the previous slide? Just so
Yes. This one?
Yes, actually, in this slide, I have a doubt like, what is this dimension of this tensor basically? Is it 2D or?
No, this is the 3 dimension. This is the stress energy momentum tensor. I know your question. So here we are measuring X, Y, and Z. This is something I won't explain right now because we will go out of time. This is, you go to my channel, I will send you the link later. This is called stress energy momentum tensor. This is a 4x4 matrix. Okay, Rajkumar. And each one of them has got 3 axes, X, Y, and Z. So it is measuring the pressure and the stress on each one of these surfaces.
Okay, sir, got it.
It is purely a Cauchy tensor or a stress tensor. Nothing to do with that, right? Okay.
Yeah.
So this is actually what causes the curvature. And we can now measure the curvature with Einstein field equation. So gravity is now a curvature. It is not a force. Okay. Now, when we talk about that, the first question that comes to our mind in astroscience is that what is actually a black hole, which has got the highest curvature? So a lot of people make this kind of understanding that black hole sucks everything like a vacuum cleaner, or it takes everything inside it, or black holes are small holes in the wall. No, it is not. It is the same thing, just as I have mentioned, Jupiter causing a big curvature, Earth is causing a less curvature, okay? So matter causes the curvature. So if there is a huge amount of matter in a small amount of space, it causes a curvature. And this is what is a black hole. Black hole is just a region where space-time is, and the curvature is so high that even you and me, forget you and me, light cannot escape. So here you can see. So now are you getting an understanding that a black hole as itself, there is nothing extraordinary or special. It is just a curvature, but it has got a very high curvature. And how do we measure the curvature? Ricci curvature, metric tensor, all those things. You now know that Einstein field equation, the left-hand side talks about the curvature, right-hand side is the matter. So now my question to you or to everybody is that how do we measure the curvature? The left-hand side of the Einstein equation. And what is the matter that joins in? What is the matter that measures it? That is the stress energy tensor, which is this equation, which Rajkumar was pointing out. This one. Okay. Now, if I say that the matter is very heavy, for example, if the matter is very heavy, what do we mean by matter is very heavy? That we will come. But let us now go to astrophysics and let us try to understand what is this heavy matter all about. Okay. Now, if I go to night sky, first of all, my question is that we know that black hole is caused by a collapse of a star. You all agree to this? Rajkumar, Karan, Swapnasagar, you all agree?
Yeah.
That black holes, okay. Now, question is that can any star become a black hole? I can just go to night sky and tell this star is a black hole. No. That means now try to understand from Einstein field equation. Star is the mass source which is causing the curvature. Are you getting my point? All of you. Star is the mass which is causing the curvature, right? So how dense or how intense a star would be to become a black hole? That is the biggest question. Now here you see, if I take up any star in night sky, it cannot become a black hole. So first is that a star has to have an initial mass less than about 8 times of the sun, but still it will not become a black hole. It will become a white dwarf. My screen is visible, Rajkumar. The white dwarf and this arrow yellow star, it is visible. You can all see that?
Yes.
Okay.
It's visible.
Okay. First thing is that we
Yes,
are...
sir, visible.
Okay, great. The first thing that you need to understand is that how much matter should be there to create a black hole, so that my right-hand side of the equation, stress energy momentum tensor, can measure it. So first is that it still cannot become a black hole. It becomes a white dwarf. Now, you might have asked a question, sir, white dwarf, how dense it is? Here is the answer. So if you take 1 teaspoon of white dwarf, it will be the size of one full-grown African elephant. Yes, you are right. If it is 1.44 times the mass of the sun, it will undergo supernova. Amarpal Singh, I think you have got right point. So if I take a white dwarf, which is the size of a Earth, okay, it is 200,000 times denser than the Earth. Try to understand, all the viewers, what we are talking is not only about how big it is, but how dense it is. And this density should be in a very small space. That is only when things become black holes. So 1 teaspoon of white dwarf is going to weigh like a 1 full elephant. Point number 2. If the star is between 8 to approximately 20 to 20 times the sun's mass, it will explode in a supernova and leave behind what is called a neutron star. Neutron stars are extremely dense, extremely dense. I will show you an analogy which you will understand. Still, we have not reached black hole. Remember, white dwarf, then to neutron star. And neutron star looks like this. 1 teaspoon of neutron star is equal to 1 Mount Everest. Still, it is not a black hole. Understand this. So we have reached the second stage, the neutron star. Neutron star have got a lot of properties, etc. Yes, 1.44 is known as the Chandrasekhar limit. I will come to that. Right, you are very right, Mr. Singh. So still we have not reached black hole, but it is very heavy. It will weigh just like Mount Everest. Okay. Now you see this star, if it is 20 to 25 times the sun's mass, I mean to say our sun, then there are 2 ways. Either it can directly collapse to a black hole, okay? Or if a neutron star, average neutron star, if I take it, if it exceeds something which is called Tolman-Oppenheimer-Volkoff limit. I'm not going into this. This is a limit. This is a number, say X or Y or Z. Then it can become a black hole. So there are 2 possibilities. Excellent coverage by your side. Thank you, Mr. Singh. So there are 2 things. One is that a star can directly collapse to a black hole if it is 20-25 times the sun's mass, or a neutron star, if it exceeds the limit, TOV limit X or Y, whatever the number, then it will also collapse to a black hole. So remember, it is not important about the black hole, but how much compact things are, right? And how small it is. So that is why I have shown you 1 teaspoon of neutron star is 1 Mount Everest. 1 teaspoon of white dwarf is equal to 1 elephant. That means very small. Teaspoon is how much? I think 5 millimeter. You can take a spoon from your kitchen. I hope your mother is not angry, and tell your mom that, Mom, I'm going to weigh a neutron star, and check her reactions. So this is very small, right? Okay, so this is how it is. It is so dense, so much dense. Now we come to the next topic, which is very fascinating, although this is a quite detailed one, but I will try to cover how black holes are formed. Now, in this part of our session, what I'm trying to give you a very basic understanding of how black holes are formed. Black holes undergo many billions years of metamorphosis, which we call, but this is how it is formed. The first thing that you need to understand that anything can turn into a black hole. I don't know, my height is around 5 feet 8 inches or something. Shubhankar is very tall, I know him. So if I am reduced to a size of 1 femtometer, you know how much is 1 femtometer? Very small. Then my body can turn into a black hole. No, I don't want to become a black hole because I have a lot of work to do in science. So it can turn into a black hole. So what I'm trying to tell that if you squeeze the entire mass of sun into a small, what we call this peanut, in Bengali we call it chinabadam, right? So that also can turn a black hole. That means you need to compress a huge amount of mass in a small thing, then that thing will turn into a black hole. Okay. So first of all, understand this one, this picture. So if the first one, this is a star and this star consists of a lot of hydrogen atoms. Okay. On the right hand side, another arrow which I'm showing, these hydrogen atoms, they fuse and become what are called helium atoms, and it gives out energy in the process. And this is what is called nuclear fission. Okay. Sorry, nuclear fusion. Fusion and fission are different. This is called nuclear fusion. So the stars are not burning fire. They are actually creating heat and energy by what is called fusion. The next stage is this one. Stars, as I told you, are very big nuclear reactors. So they continuously convert hydrogen to helium, hydrogen to helium. Now, everything is fine till the time when there is enough hydrogen to convert to helium. But as I told you earlier, that stars are massive. That means they also have a very strong gravity. And here you can see there is an inward and there is an outward push. Now, here is a point I would like to make all of you understand. This is a relativistic study we are doing. Okay. In Newton's law of gravity, gravity is always attractive. Okay. That is why in Gauss's law of gravity, you will see arrows pointing downwards. It's not pointing outwards, because it is always attractive, not repulsive. But Einstein's gravity is repulsive also. That is why in Big Bang, it all repulsive and our universe, Brahmand, was created. Okay. So what I'm trying to tell is here that when the star has nuclear fusion reactions going inside it, the energy from these reactions keeps pushing out, pushing against the gravity of the star. So just for example, you're blowing up a balloon, the air is pushing out. So outward force, that means energy from radiation, is equal to inward force and all is good. But the problem starts when a star has used up all the hydrogen. As I told you, hydrogen is constantly used up. All the hydrogen is used up and converted into helium. So that means there is no hydrogen equal to no nuclear fusion equals to no energy, right? This is the second stage that we reach. Then you see here, this is, I have collated in only one diagram. But what you can see is that the helium inside, can it convert in something else? And what exactly happens? So the star starts reducing in size. Here you can see the star is contracting on the first line. All the helium is contracting, and it turns from helium to lithium. Okay, but remember, this cannot happen overnight. Hydrogen is over as helium, it takes time. So due to the new energy from fusion reactions to helium, the star starts again to expand. So it is contracting, expanding, contracting, expanding. And in this way, it expands and becomes what is called a subgiant star, and then what is called a red giant. So red giant, remember, have cooler surfaces than the main star because of this, and that is why they appear red than yellow. Because of this, the color is red. And then there is something which is called a supergiant stars, that is out of the main sequence star that have run out. And it goes on and on and on and on until the helium is totally exhausted. Then what we find, this iron absorbs the energy generated by nuclear fusion, and instead of resisting gravity, all the energy is absorbed and the star starts contracting. You can see that entire helium is taken and now it is coming small and small and small and small. Okay. Now, if the star is not very big, then it will stop shrinking, and the electrons, particles with negative energy in the atoms, starts repelling. because same charges repel. And this force resists the force of gravity. And this actually results in what is called a dwarf star. We have seen a dwarf star, white dwarf. So this is how a dwarf star is actually formed. Right? Is it all okay till now? You're enjoying this? How the black hole is getting formed? Rajkumar and Mr. Singh, everybody? You're all, I mean to say, it is not going too fast,
Yeah.
right? Okay. Now here you can see what happens at the end. At the end, what happens that the star becomes so big that even the electrons cannot stop shrinking. And in this case, the electrons combine with the protons, particles with positive charge, in the atom and form neutrons, particles with no charge. As a result, what we got is a neutron star. So electron degeneracy, no two electrons cannot occupy identical states, and the pressure is basically what forms a neutron star. And then finally what happens is this one. If the star is extremely massive, even the neutrons also cannot stop it from collapsing the entire star, and it now contracts to what is called a small point in space, which is called a black hole. So this one was electron degeneracy. This is called neutron degeneracy, and this comes from this Pauli exclusion principle, that no two neutrons can occupy identical states. So for masses greater than 3 solar masses, even neutron degeneracy cannot prevent, and it continues to form in what is called a black hole. So this actually completes our discussion in understanding how and where and under what conditions black holes are formed. Okay. Now we come to understand in the final part of our discussion today, some of the astronomical and astrophysical objects. Now, why I am showing you this, I hope you have infinite density with infinite mass in simple terms, absolutely. And this point is known as singularity, where the entire physics breaks down. You're absolutely right, Mr. Singh. So what happens here is that now that we have understood space-time curvature, Einstein Field Equation, tensors, and we know that the very dense mass in a very small space causes the space-time go to infinity. Yes, Rajkumar, tell me your question.
So this is a complete event that you have explained, and that can be happening any point in the universe, right?
Any point in the universe, yeah. Provided the conditions are meeting, right?
Yeah. So basically, I've heard some theory like in the middle of the galaxy, it's usually happen. The quality of getting this find in the middle of the galaxy. Is it
yes,
true?
Black holes are somehow found at the center of the galaxies.
So why is there basically not? Why in this is center, not in the other part of the galaxy?
Well, in that case, I have to explain a lot of things. First, let me show you these things. Then I will come to that part. At the end, I think I can tell you why black holes are at the center. It is still actually under research. We actually don't have an idea that why black holes are at the center. Okay,
yeah,
this
the
is
quality is very, very less. Like it can be in the any part of the
it can be until and unless we find out the proper evidence that why it is at the center and not anywhere.
Yeah, exactly.
You got the point. So we need to actually find out a proper evidence. Till now it is I mean to say there is no proof. One thing I can tell you, Rajkumar, that why it is at the center of the galaxies mostly. Primary, I can tell you that because the gravitational attraction and galactic formation. Because supermassive black holes are likely to form through the merging of small black holes. Right. So at the center of the galaxy, the gravitational attraction is also quite high. Okay, that is why that it is formed due to these types of attraction. And also remember that as galaxies, they evolve, I mean to the spiral galaxy or different types of galaxies, these accretion process allows black hole to grow and influence the surrounding atmosphere. And orbital dynamics also plays an important role, that the galactic center is very dense, right? So dense core of the galactic center actually follows through funneling matter towards the center. So this is how actually things happen. Although we don't have a kind of a proper evidence that why it is so, because it is still, undergoing. Right, Rajkumar?
Yes.
I think I can answer few of your questions.
So basically, so we can say it's a point where maximum condition gets satisfied actually.
Maximum condition, number one, gravitational attraction. Number two, accretion of matter. So a lot of matters are being accreted. Orbital dynamics is very stable. Okay. And nearly all large galaxies, Milky Way, for example, Sagittarius A star, we have found through observation that galaxies do have black holes at the center. So there is a correlation between galaxies, what is called central bulge mass, right? And it suggests a deep connection between galactic formation and black hole evolution. So both of them actually satisfied that. So that is why till now we have found this to be okay.
Got it. Thank you, sir.
Okay. Now we will just quickly look over some of the what we call the astronomical objects and astrophysical objects. Now there is a distinction between what is called an astronomical and astrophysical. Astronomical means what we see through telescope. And astrophysical means through which we study. We use mathematics or physics to study those things. Not much. I will just tell you some very important. First of all, let us understand what is the difference or relation between astronomy and astrophysics. So astronomy means where we are studying the celestial objects. Okay, observation, telescopes, etc. So we use these things in order to study. So astronomers, we use powerful tools like telescopes, etc. to observe things. Okay, remember that astronomy is very old. Astrophysics came much later. First, we started all observing. Galileo, Kepler, even Tycho Brahe, all of us, they have observed things. But analysis came much later. Astrophysics uses the principles of physics to understand things, right? Very simple. So astrophysicists are using the physics, using the mathematics to do that. Okay, so it explains why these things actually happen. Okay, so the correlation is astronomy is basically observation and study. Astrophysics is basically the physical principles. Astronomy uses telescopes. Astrophysics uses mathematical models like simulations, etc. Astronomy includes both observation and theory, and this is applying physical principles. Okay, now we come to a very important and interesting phenomena, which is called red giant and red supergiant. I explained this was responsible for black hole formation, right? Now hear this out. This is called a red giant. Red giant is something where it is a large stage of the star, because until we get a red giant, we won't be able to get to black hole, because that is the fate of the star. So the temperature is huge, 5,000 Kelvin. Okay, and it grows and grows and grows much larger than its original size. Also, there is a hydrogen is the core and the forcing fusion to occur. So this is what is a red giant. It is a late star, and it is like low to medium star like our sun. Okay, now you see what is red supergiant. It is more or less similar, okay, is massive, but it grows to much larger than red giants. That means it is much more bigger. Surface temperature is around about 5,000 kelvins, nuclear fusion stages, and explodes in a spectacular supernova, and it might lead, again, there's a probability to form a neutron star or a black hole. So that is why at the stage when we were forming, I showed you that why from red giant we get into red supergiant. And then when it explodes, it becomes either a neutron star or a black hole. So again, a comparative, I am just quickly going through. Red giants are low, red supergiants are massive, red giants are large, red supergiants are significantly large. This looks less luminous, these are much more luminous, and red giants end as white dwarfs and red supergiants become supernova. Okay, now we come to, I am skipping this part, this is more or less the same. The next important thing, and most of the students, they get confused, it is called event horizon and Schwarzschild radius. Very important concept in astrophysics. Now, event horizon, I was just listening to, before coming to this podcast, to Professor Leonard Susskind, wonderful podcast. So event horizon, he was telling, imagine this, that you are rowing a boat. Okay, you're rowing a boat along a stream. There's a water, okay? The water is flowing, and then you come to the edge of a hill and you fall. So event horizon is basically the edge of the hill, okay, where you might fall. But when you're flowing, the water is flowing very high, and as you get to near to this edge of the hill, it is called event horizon. So event horizon is basically a point after which there is no return. Okay, once you fall within the event horizon, you can see nothing, you cannot escape. So it is a one-way membrane, and it actually conceals, that means it hides the rest of the world from black hole. So once you reach event horizon, nothing is there. But remember, event horizon is a mathematical concept. It is not a physical thing that you can touch and feel. Okay, Schwarzschild radius is also a mathematical concept. Schwarzschild radius, what it tells, that the distance from a black hole center at which the escape velocity of any object equals the speed of light. That means Earth has a Schwarzschild radius, Jupiter has a Schwarzschild radius, Mars has a Schwarzschild radius, even my body has got a Schwarzschild radius. That means theoretically it is a calculation, it is a radius beyond which nothing can escape. Okay, so remember, it is not a physical barrier. Unlike event horizon, the Schwarzschild layer is not a physical boundary. It is a theoretical concept which Carl Schwarzschild actually developed when he was in Second World War. No, it is First World War, 1915. He wrote a letter. I have made a wonderful video in my channel where you can see what this letter is all about. So here you can see the difference. Event horizon is a boundary. Schwarzschild radius is a mathematical calculation at which escape velocity equals to the speed of light for a non-rotating black hole. Now, why I have written non-rotating black hole? I would like to tell you, there are different types of black hole: a rotating black hole, a non-rotating black hole, a charged black hole, a non-charged black hole, different types of things. Okay, so this is ideal for a non-rotating black hole. Scope is event horizon applies to all type of black holes. Schwarzschild radius applies to non-rotating uncharged black hole. Okay, and event horizon is basically a physical thing which acts as a boundary, and Schwarzschild radius is basically what is called a mathematical derivation, which tells it that if you go and calculate the Schwarzschild radius of Jupiter, Saturn, etc., then you get actually the escape velocity beyond which light cannot escape. Okay, here it is. It has got a relation to black hole. It determines the size, observable effects, and this is the calculation 2gm by c square. Okay. Now, there is another important thing which is called dark matter and dark energy. A lot of researches nowadays are going on. So dark matter is basically a form of matter that exerts gravitational forces but does not interact with electromagnetic forces. This is important. It does not interact with electromagnetic forces. Dark energy is a form of energy that actually creates the accelerated universe. So if you see the world is expanding, the universe is expanding, people say that it is because of dark matter. Again, it is a hypothesis, nothing has been proved. So here you can see that it has dark matter exerts gravitational forces. It is important for structural formation, and it is important potential candidate for axions and sterile neutrinos. What is an axion? I won't explain right now, because axion, if you go to my channel, you will see there is a specialist from Durham University, England, who has I have taken an interview podcast for about more than 1 hour, what are called axions. These are quasi-particles. It relates to particle physics. Dark energy is something a little bit different. Dark energy is telling that dark energy is a mysterious form of energy. Again, it is hypothesized to permeate all of space and drive the accelerated expansion of the universe, right? So it is something important for cosmic expansion. Okay, observed acceleration. Dark energy constitutes about 68% of the total energy. So here is a comparison. Dark matter is a form that exerts gravitational force. Dark energy is energy driving the accelerated universe. Dark matter is responsible for affecting the motion of galaxies and formation. Dark energy is uniformly distributed. Dark matter is detected indirectly through gravitational effect, and dark energy is uniformly distributed, and it is responsible for the accelerated universe. We come to the next important thing, which is called what is an Eddington limit and Chandrasekhar limit. This is actually what Mr. Singh was telling. So these are two limits, very important for astrophysicists and science people to know. This is by Arthur Eddington. This is by Subramaniam Chandrasekhar. So Eddington limit is actually talks about luminosity. That means brightness of a star. Okay. So maximum luminosity a star can get. That is the maximum. If you think of a torch light, then how much bright a torch can be? That is Eddington limit. Okay. I'm not going in the mathematics. At the Eddington limit, this radiation counteracts the gravitational force pulling matter inward, and balance of forces. When the radiation pressure equals the gravitational force, the star is the Eddington limit. This is about luminosity. Chandrasekhar limit is totally different. Chandrasekhar limit is the maximum mass that a stable white dwarf star can have. And if it crosses Chandrasekhar limit, which Mr. Singh was telling, it collapses into it can be a neutron star or it can be a black hole. And this was discovered by Subramanian Chandrasekhar when he was going from India to England over a ship. He was sailing to England. During that time, we did not have this fast aircraft. So he was sailing to England, and this actually caused a lot of fight with Arthur Eddington, who did not actually agree to that. So if the mass of a white dwarf exceeds Chandrasekhar limit, then it will collapse. Now, it can collapse into anything, not only black hole, but this is the limit. Okay, electron degeneracy pressure is also there. So here you see Eddington limit is related to luminosity and radiation pressure balance. Chandrasekhar limit is the collapse. Eddington limit involves balance between radiation. Chandrasekhar limit involves balance between electron degeneracy and gravitational forces. If a star exceeds the Eddington limit, it leads to mass loss. If the star exceeds the Chandrasekhar limit, it can become either a white dwarf or a neutron star or a black hole. Coming to the next part, there is a very important concept called redshift and blueshift. Very simple. Redshift happens when the wavelength is increased. That means it is longer and longer and longer, and it looks red. And this is because we have noticed, this is not only mathematics, we have seen what is called a redshift. So cosmological expansion causes redshift. So light escaping from a strong gravitational field is redshifted. So a strong gravitational field is what it is actually pulling things, right? So the light frequency is longer. So that is why it is called redshift. Exactly opposite is the blueshift. When the wavelength of light is decreased or shifted. So blueshift is actually caused by the motion of the object moving away from the observer. Okay, so this is moving away and this is moving towards. So light moving towards the strong gravitational fields is causing a blueshift. So here you can see redshift is moving away, blueshift is moving towards. It is redshift is associated with the expansion of the universe. This is moving towards the observer. And this is found, redshift is found where the galaxies, and this is more in cosmological scale. For example, Andromeda galaxy, which is coming close to Milky Way, we can see the blueshift. Coming to the next quickly, galaxy and nebula. Galaxy is a massive gravitational bound system. It is responsible for gravity, and it contains nebula. So galaxy contains nebula. Okay. And nebula is what? Nebula is a giant interstellar cloud composed of hydrogen, etc. And there can be different types of nebula. Okay. For example, emission nebula, reflection nebula, planetary nebula, whatever. And the size can vary. So galaxies are very big, typically huge, thousands of light years. Nebula are much smaller. Galaxies have complex structure. Nebulas have intricate internal structure. And the star count, they contain millions and trillions of stars. Nebula can have few to thousand stars. And the composition of galaxy consists of gas, dust, matter, etc. And nebula is primarily composed of gas, but it can vary density and temperature. This is the last part of our discussion. What is a meteoroid? Very interesting. What is a meteor and what is a meteorite? So these are three important phases. First of all, what we see through telescope is a meteoroid, a small rocky substance in the night sky which is going around, right? Small boulder, it looks like a rock. The next phase is a meteor. Okay, so first meteoroid, then a meteor. Meteor is something when something is falling inside the earth. will mean Bengali we call it ulka path, which we can see that streak of light. This is called a meteor. When a meteoroid enters an Earth's atmosphere, it is called a shooting star, and we can see it through naked eye. Many of us in villages, etc., at night sky, we see meteor. But meteoroid cannot be seen in naked eye. And meteorite is what finally falls. Okay, that survives its passage, and it can vary greatly inside. Now I will show you something. Phase 1 is the meteoroid, the starting point. It is an object in space. Then comes the meteor, which actually falls in the visual phenomena. And third is the meteorite. That is finally what is left over. Here is a comparative understanding. Meteoroid exists in space. Meteor comes, and meteorite is what reaches the Earth. Here you can see location outer space. This is Earth atmosphere. This is Earth surface. Size is, it can be grain of a sand, or it can be very big. Phenomena, it exists in small object, as a small object in space. This can be seen when it enters the Earth, and it emits those emission of light, and finally it lands over here. So this is used, meteorite is used to understand what materials are there. Meteor is study because atmospheric entry, why it is causing light, etc. And meteorite is finally which is there on Earth, which is causing the solar system, and then we take it back into the laboratory and then we study. So that's all for today's. I think I have just taken 10 minutes more time. So you can subscribe to my channel Physics for Students, which contains this type of videos, and you can also subscribe to my other channel, General Relativity Explained. And this is typically only on general theory of relativity, Einstein-Hilbert action, and a lot of things. This I have started very lately, just from January onwards, where I am building those things. So Shubhankar, I am all done with my presentation. I wait for the feedback.
Yes, that's a wonderful presentation. If anyone has any question, feel free to ask, sir.
Good evening, sir.
Good evening.
This is Amarpal Singh, astronomy educator, astronomer from BBS Planetarium, Gorakhpur, UP. Sir, you are always most welcome at the planetarium, sir. You are also doing great, sir. Great, extraordinary, sir.
Thank you. I will visit your planetarium, and I wish to see you in sometime in the near future.
Thank you, Agnira team, for your wonderful session here, and special thanks goes to sir as well, because it was a wonderful session, excellent session, which has been made by sir and sir only, sir.